Guys, so I think we are live. So today, I'm going to start. We're going to start understanding what disjoint sets are. So disjoint set data structure we will be understanding, and we'll also be solving some problems based on this disjoint set. Okay, so okay, let me create a class also for this. Disjoint set is defined as one that keeps track of set of elements partitioned into a number of disjoint non-overlapping subsets. Okay, so basically like uh, how to draw. Okay, okay. So basically, what disjoint set is defined as one that keeps track of a set of elements partitioned into a number of disjoint subsets. One is that one is defined as one that keeps track of a set of elements partitioned into number of disjoint subsets. Mm, a union find algorithm is an algorithm that performs two useful operations on such a data structure. Find, determine which subset a particular element is in. This can this can determine if two elements are in the same subset. Determine which subset a particular element is in. Okay. Find, determine which subset a particular element is in. This can determine if two elements are in the same subset. Union joins two subsets into a single subset. Okay. Here first we have to check if the two subsets belong to the same subset. If not, then we cannot perform union. Joins two subsets into a single subset. Here first we have to check if the two subsets belong to the same set. Hmm. If not, then we cannot perform union. If two subsets belong to the same set. Hmm. Okay, these are the applications, but where is the introduction? Student set. Okay, yeah, this will be useful. Um, Two sets are called disjoint sets if they don't have any element in common. The disjoint set data structure is used to store such sets. Okay, so let's say if I have one. Okay, uh, so one, two, three. I have, and I also have four, five, and six. So uh, no element. So I can call this A and I can call this B. And A intersection B is equal to phi. Phi means empty, nothing. So if we intersect, this intersection means common elements in both A and B. So there are no common elements, so we get a phi. So we can say A and B belongs to the disjoint set. So A and B are basically disjoint sets. There is nothing common. So the condition thus needs to be satisfied is A intersection B should be phi. That's the condition thus need to be satisfied. Okay. Merging two disjoint sets to a single set using union operator. It suppose following operation: merging two disjoint sets, finding representative, finding representative of a disjoint set using find operation, finding representative of a disjoint set. Uh, okay. Check if 12 belong to the same set. We mainly find representative of both and check if if same. Check if 12 may belong to the same set or not. We mainly find representative of both. Consider a situation with a number of persons and the following tasks to be performed on them. Okay. With a number of Consider a situation with a number of persons and following tasks to be performed on them. Add a new friendship relation. That is, a person X becomes a friend of another person Y. That is adding new elements to a set. Find whether X is a friend of individual Y, indirect or direct friend. Okay. Okay. That okay. Find whether individual X is a friend of individual Y, direct or indirect friend. Okay. We are given 10 individuals, say A, B, C, D, E, F, G, H, I, J. Following are relationships to be added. Okay. Given queries like whether A is a friend of D or not, we basically need to create following four groups and maintain a quick, accessible connection among group items. Okay, so let's refresh it. A and B are friends. So they are group 1, A and B, B and D. So yeah, let's okay. Group 2, CFI. Group 3, EG3. Group 3, EG. Group 4H. Group 4H. Okay. So these are friends that are divided into separate groups, and now we need to perform some operations. Find whether X and Y belong to the same group or not. Okay, given query is partitioning the individual into different sets according to the group in which they fall. Okay. This method is known as disjoint set union, which maintains a collection of disjoint sets. Maintains a collection of disjoint sets, okay, and each set is represented by one of its member. Hmm. Mhm. So you are saying partitioning the individuals into different sets according to the groups in which they fall. This method is known as disjoint set union, which maintains a collection of disjoint sets, and each set is represented by one of its member. Hmm. So basically, we are disjoint set data structure basically divides the individuals into a specific set where they belong. Okay, and we can just find out if two members belong to the same group or not. Okay, and also we can join two groups if initially they are disjoint and after some time they can be joined. Okay, how to resolve sets? Initially all elements belong to different sets. Okay, so each element belongs to a different set. After working on the given relations, we select a member as a representative. Mhm. Check if two-person are in the same. Check if two persons are in the same group. If representatives of two individuals are the same, then they are friends. If representative of two individuals, okay. After working on the given relation, we select a member as a representative. Okay, so every group has a representative, and uh, every sub member of that group can look to representative as his own identity kind of thing. Okay. Data structures used are array. An array of integers is called parent. An array of integers is called parent if we are dealing with n items. Ith element of the array represents the ith item. Array. An array of integers is called parent if we are dealing with n items. Okay. Ith element of the array represents the ith item. More precisely, the ith element of the parent array is the parent of the ith item. These relationship creates one or more virtual trees. Array. An array of integers is called parent array. If we are dealing with n items, the ith element of the array represents the ith item. More precisely, the ith element of the parent I array is the parent of the ith element is the parent of the ith item. Okay. Okay. So basically, let's say if I have like this kind of this tree, one, two, and three. So if I create the structure, one doesn't have parent, so minus one. Two has parent one, three has also parent one. So this is the structure. Okay, parent array, right? This is my parent array. Okay, this makes sense. It's easy kind of. It's not that tough. Okay, tree. It is a disjoint set. If two elements are the same tree, then they are in the same disjoint set. Okay, the root node or the topmost node of each tree is called representative of the set. So here one is kind of the representative here. One is the representative here. Okay, my English. Wait, representative here. There's always a single unique representative each of each set. A simple rule to identify a representative is if I is the representative set, then parent of I is I. Okay. So for a representative, parent will be itself only. So if I have 1, 2, 3, so I's parent will be I only. Okay. 1. Hmm. If I know the representative is set, then it can be found by traveling up the tree until we find the representative. Recursively, we can travel until we find the representative. Let's say if I have 4, then 4's parent is 2, then 2's parent is 1. Or recursively, we can figure out 4's the representative also. Operations on disjoint set data structure. Find. Okay. The task is to find representative of the set of a given element. The task is to find representative of the set of a given element. That representative is always the root of the tree. Find. Okay. Okay, give me 2 minutes. I'll come back in 2 minutes. Okay, guys, I'm back. So, Emma, so our stream is live, right? This stream is live. Okay, it's live. Oh, but it's complete screen as well. Okay, so the find is used to represent find representative of a given set of find representative of the set of a given element. The representative is always the root of the node, so we implement find by recursively traversing the parent array until we hit a node that is the root parent of itself. Okay, that is simple, right? That is simple. The second one is union. The task is to combine two sets and make one. Okay, I think find is quite easy, and I think union will have to think quite little deeper to understand exactly the use case of union. Let's go. The task is to combine two sets and make one. Okay. It takes two elements as input and finds the representative layer sets using the find operation. Okay. And finally puts either one of the trees under the root and finally puts either one of the trees under the root node of the other. Okay. Okay, so let's first implement this data structure. So it has find and it has unite, right? Hmm. It also has a parent array and so where are all the sets here? Hmm. Hmm. Okay, I think it's simple. So we will just implement this data structure here first of all. Okay, I'll make this screen a bit big. Okay, let's create another class. Public class disjoint disjoint sets, and here we will have our parent array private private int array parent, right? And so whenever we will create the data structure, so we will define the size of total nodes, initialize the parents, and initially everybody will be the parent of itself. And here, like logically, always we write I less than equal to n. That is our simple motto, right? But the same thing can be achieved by writing something like I not equal to n. That is equal to I plus but the problem here is, since it will work here because I is increasing singularly. But if let's say I increases by 1, 3 or 5, so I can cross and it can continue to do for indefinitely. So we have to keep that thing in mind. But for now it will work, right? So we can write this. And it's kind of similar to while loop. Gotcha. So here we'll assign parent of I equal to I, right? So I is everyone is parent of itself. Okay, and then we will have two operations. So first one is I'll create an interface for this public interface. I disjoint set, joint sets. It's a clean code practice, so clean to fine. So I'll take an element u and I'll return an int, and second one will be union, that I'll take two elements, int u and int u and int v. And yeah, I'll just do union. I'll not return anything from there. And yeah, okay. So these two things are done, and now we have to implement those. So I'll just here write I disjoint set, and now it will like complain because I have not implemented these two functions. So yeah, so I'll just implement those here. So first one is find. Okay, okay, find, and it will have just a single element, right? Into you. So what I'll do? Okay. So find you will what actually find you will do is uh so uh so so I'll go to parent of you, right? And parent of you, and the parent of you will be equal to parent of you, right? And so uh, okay, so this is the parent of you, right? Parent of you will store the parent of you, and we have to find the representative, right? Which means the ultimate parent. So okay, okay. So uh, if parent of u is equal to u, here what this means, the index, right? So we have figured out, right? Basically, like what I'm doing is okay. So I'll explain this by the draw, like what's my thought process is. Uh, so let's say if I have a structure like this: 1, 2, 3, and something like 4 here, right? I can have this structure. There's nothing wrong with this. So one's parent is 1, two's parent is 1, three's parent is 1, four's parent is 2. And I have the question to find ultimate parent of 4, right? Find representative of 4, right? So what will happen, right? So I find parent of 4, right? So it comes out to be 2. So what I can do, I can check the index is 4. So index 4 is not equal to 2, right? So if it's not equal, then I have to find the parent of 2, which is 1. Find the parent of 1, which is 1. Now whenever I find the index equal to 2, well, I'll return that. So okay, so parent of u is equal to u, then I'll just return parent of u. Else what I'll do, I'll return find parent of u. So now again I call this, right? So this basically what it does is it goes to 4. 4 is not equal to 2. So again call the function. Go here, go to 2. 2 is not equal to 1. Again call the function. Go to 1. 1 is equal to 1. So it is return true. So here it returns 1. Here it returns 1, and that 1 is again returned to 4. So ultimately we get ultimate parent of 4 as 1. It's quite simple, right? It's very easy recursion. Can understand it. Easy problem. Very simple. Base condition is always this only, right? So it's kind of simple recursion. It's easy to understand. So find is implemented. Next we will implement union. Okay. So in union, what we will be doing is that the task is to combine two sets and make one. It takes two elements as input and finds the representative of their sets using the find operation, and finally puts either one of the tree under the root node of another tree. Okay. So what we do is basically we point. So let's say, okay, so I'll just explain it by drawing. It's also quite simple, right? It's not that tough. Okay, so I have 1, 2, 3, right? And I have 4, 5, and 6. Okay, it's 6, then I'll create a 5 here. Okay, okay. So now if I have to union them, right? So what will I do? So 1 is the representative and 4 is the representative, right? So I'll just attach 4 to 1. Simply I'll attach 4 to 1. Make now and update the parent of 4. Also I need to update the parent of 4 to 1, right? And that's it. I mean that is update parent parent of 4 to 1, and that's it. That's how union is done. It's that simple. So I think you got it, right? What needs to be done here? Okay. Okay, so next we will do this something like with the hmm, so okay, int parent of u is equal to find, and I'll pass u, and similarly int parent of v is hmm, ultimate, not ultimate. So I mean representative. It should be representative. Representative present SN representative of you and representative of V, make it V. So what I'll do, hmm, so I'll attach the representative of U to V. Uh, So what I'll do, so the only step that I need to present is parent of the representative of U is equal to representative of V. And that's it. That's it. That's how we will do the union. That's it. That is it. There's nothing more to be done here. And that's how we have, I think, completed the disjoint sets. That's it. And I think we can now answer some questions. Okay. So we will like, okay, so we'll answer some questions here. Okay. Uh, okay. So let's write the question into size equal 5. Mm, my disjoint sets equal to okay, and pass size, and next thing union joint sets or union uh 0 and 1, 0 and joint size dot union 2 and 3. I'm assuming as from 0, right? So console dot right line, and oops, oopsie, can make it little big, and okay, so join sets dot find if so 0 and 1 is in one set, 2 and 3 is in different set. So if I write 0 is equal to join sets dot find 1, they should be false, right? Okay. Console dot read key, boom boom boom, control shift P. Let's wait for the program to compile, and we will be able to see this. Mhm. Mm, false. Wait, what? It's true. Oh, obviously 0 and 1 are in the same set. This is true. And if I write here 2 and again I compile, it will be false. So that's working fine. Right? It's working fine. Okay, so we have basically understand a simple thing, right? What needs to be done here. Can we can so so currently what's happening is, let's say that tree is there are further optimization that we can do here, right? There are further optimizations that we can do here, and we need to do those optimizations, right? So here in the diagram, it's mentioned that the above are naive and worst case time complexity is linear. Huh, okay. They are naive and their worst case time complexity is linear. The trees created to represent subsets can be skewed and become like a linked list. Following is an example of worst case. So basically what it is saying is that, let's say the tree is like this, right? So if I have to find the parent of 0, so I have to traverse to 1, then I have to traverse to 2, then I have to traverse to 3, and then again I have to traverse to 2, then again I have to traverse to 2, 1, then again I have to traverse to 0. No, I mean, only single time I have to traverse, so 0, 1, 2. So linear time complexity, right? The time complexity will be O of n, big of n. Can this be improved? That's the question, and the answer is yes. So how? Optimization, path compression, and union by rank size. Okay, so we need to understand the path compression and union by rank and size now. Okay, okay. So um, Hmm. The main idea is to reduce heights of the tree representing different sets. We achieve this with two most common methods: path compression, union by rank. Okay. What is the main idea again? The main idea is to reduce heights of trees representing different sets. Okay, so we need to reduce the height of tree, obviously, because we have to traverse to lot of time. So if we reduce the height somewhat, then our complexity will be easy. Our traversal will be easy. Okay. We achieve this with two most common methods: path compression and union by rank. Okay. Path compression used to improve find. The idea is to flatten the tree when find is called. The idea is to flatten the tree when find is called. Okay. Flatten. So you understand, right, what flattening of the tree means. So flattening of the tree means that so let's say if I have tree like this, 1, 2, 3, and 4. So what I can do is, flattening means I can do something like this: 1, 2, 3, 4, right? Now as you can see, what is the difference between these two trees? uh, One difference that is visible to me is height of h1 is greater than height of h2. So height is reduced, obviously, right? Height is reduced. What is the second visible difference that I can see? I can see that 2 was the parent of 3, now 3 is, but this is not uh, kind of relevant to us because we are uh, only concerned about the ultimate parent, right? We are not considering the current parent or above parent. We are only worrying about the ultimate parent. So ultimate parent is same, right? And height we have reduced. So this is a win-win for us. You can see. Okay. So we can do this, right? Path compression. So this is called path compression, obviously. How many viewers I have right now? Concurrent viewers. Uh, hmm, no concurrent viewers. Okay, no problem. So the idea is to flatten the tree when find is called. When find is called for an element x, root of the tree is returned. Okay. Find operation traverse up from x to find root. The idea of path compression is to make the found root as parent of x. The idea of path compression is to make the found root as parent of x so that we don't have to found root as parent of x so that we have to traverse all the again. Okay. If x is the root of a subtree, then root from all nodes under x are also compressed. So it's saying that let's go by the diagram. Let's Okay. So this diagram is very simple, and mm, let's understand this. Give me 10 seconds. I'll just have my drink. Actually, I'm talking that much, so my throat gets uh dehydrated. Okay. Initial tree structure. So let's say if I have this kind of tree 9, 4, 5, 6, 7, 8, and this, right? And 9 is the root. And so if the question is find for element 3. So when find is called for 3 traversal up and find 9 as representative, right? 3 will go to 0, 0 will go to 4, 4 will go to 9. And I'll find the representative, right? So what I can do is that I can make 3 I can make 3 as a root of 9, right? Parent of 9. I can make 0. I can make 4 directly as a parent of 9. So 0, 4, 9, 3. So this can be after find. Compression is applied and we can directly link elements to 9. Okay. Right. See, it speeds up the data structure by compressing the height of the trees. Okay. That is making sense. Obviously, that is making sense. It can be achieved by inserting a small caching mechanism into the find operation. Take a look at the code for more details. Caching. Uh, okay, this we can do through the code. Okay, visually you can figure out right what it is. Uh, okay, that makes sense. It makes sense to me completely. This is okay. Okay, so let's go to the next thing. Union by rank. Modifications to union. Hmm. Union by rank. Modifications to union. So this is the second. So this technique will. So there are two techniques, right? Path compression and union by rank. Like two optimization techniques. So path compression is basically when we are finding out the parent. If it's a path compression, it will be quite fast as compared to the previous one where we have to do the linear traversal. It will be kind of constant only, right? And the second thing we can do is in union by rank. And what modification we do? So when we were doing the union, right? Previously we were just attaching one in attaching any to any, right? This representative R1 and this is R2 representative, right? So I can attach R2 to R1 or R1 to R2. I was like, okay, it doesn't make any sense. It is not like it doesn't matter that if I attach R1 to R2 or R2 to I can attach any, right? But can there be slight modification we do here, which can improve our uh, which can improve our uh, or which can optimize our code a little bit. So that is called union by rank. I think by understand. Okay, let's see if there are any. Currently, there are no viewers. Hmm. Okay. Okay. So I think you have got the idea, right? I think you have got the idea how what union by rank will do. So let's say if I have two trees, one, two, three, and four, and I have another five only, right? Five and six. Let's say five and six. Hmm. Okay. Okay. Sorry. There was one chat, so I was busy with that. Okay. Now, now basically here, I think you got the point that the second optimization will be like, let's say if I'm attaching R, so this is R1, right? And this is R2. So what is better? Like if I attach R1 to R2 or R2 to R1, which will improve my find or searching better? Previously, we were not uh, concerned, right? We can attach R1 to R2 or R2 to R1. We were not concerned. But if I attach, okay, let's say if I attach R1 to R2, right? And if I attach R2 to R1, which will, like, I want that data structure to be as flattened as possible, right? I want less height. Basically, I want less height. So let's say if I attach R1 to R2, right? Then what will happen? Then I will have 5, I will have 6, I will have 1, I will have 2, I will have 3, I will have 4, right? And if I attach R2 to R1, then I what I will have 1, 2, 4, 3, 5, and 6. Can you see the difference here? Can you see the difference here? Height of this and height of this. So H1 is greater than H2, right? Now, now this tree is more flattened, so I this tree will take less operation as compared to this, which means this is better, right? Attaching R2 to R1 is better because let's say if I have to find the parent of 4, it will take 4, it will take 3. Sorry, it will take 3, it will take 2, right? It's better. It's always better. For 3, it will take 2, it will take only 1. It's better. This is better. So I think you have got the point. The second optimization is basically rank is the height of the tree representing different sets. We use an extra array of integers called rank. The size of this array is the same as the parent. Okay. If I is a representative of a set, rank I is the rank of the element I. Okay. Rank is same as height. Rank is same as height if path compression is not used. Mhm. With path compression, rank can be more than actual height. Okay. Okay. So basically, like what we are doing to, let's say, so attaching R2 to R1 is better, right? But how can I figure out whom to attach? So you can see height of R1 is greater than R2. So that which means rank of R1 should should be greater than R2. So whichever representative have the higher rank, right, should be attached to representative however the lower rank. So higher rank representative, sorry, lower rank representative will get attached to higher rank representative. Okay, and rank can be maintained by creating another array. Uh, hmm. Uh, so here. Okay, so rank is like height of the tree representing different sets. We use an extra array of integers called rank. Okay. Okay. So you need to understand the words that are written here little deeply. Rank is like the height. It's not actually the height. It's like the height. Mhm. If I is representative of a set, so let's say if I have a set and I is a member of that set, okay, then what's the rank of I? Rank of I is the rank of the element I. Okay, rank is same as height if path compression is not used. Okay, okay, rank will be same as height if path compression is not used. With path compression, rank can be more than actual height. Okay, now recall that in union operation, it doesn't matter which of the two trees is moved under the other. Okay, so this is what I already tell you. It's just repeating it. Now, what we want to do is to minimize the height of the resulting tree. Okay, as I already told you guys, right, that we want to minimize the height. So, how can we minimize the height if we attach the lower representative under the higher representative? Because, right, so, okay, that makes sense, right? Hmm. If we are uniting two trees, right, we want to do is to minimize the height of the resulting tree. I already told you guys, right, what we want to do here. Okay. Hmm. If we are uniting two trees, let's call them left and right. Then it all depends on the rank of left and the rank of right. Okay. If the rank of left is less than the rank of right, then it's best to move left under right. So if rank of left is small and rank of right is high, then left will be under right because that won't change the rank of right. That makes sense. That makes sense. That will not increase our height. That makes so much sense. While moving the right under the left would increase the height. In the same way, if the rank is less than the okay, it's making complete sense to me. Okay, let's go next. If the ranks are equal, okay, if the ranks are equal, then it doesn't matter. We can attach any to any. Uh, our non-optimal way, our non-optimal way will be followed if the ranks are not equal. Rank will be greater. Obviously, it will be. So okay, we got this right. So let's code these two optimizations into our current disjoint set. Okay. So what was the first optimization? The first optimization was path compression. Okay, so we have to compress the path, right? Uh, hmm, how can that be done? Uh, Path compression can be done in basically. So let's say this is the parent of u, right? Parent of u. Now, if parent of u is equal to u, then we are good. Else, if it is not, if it is not equal, right, then what I can do? Hmm. So, so I can store a temporary variable called uh, representative, right? Representative, and so representative will be my find parent, right? And what will I do? So parent of u will be equal to representative. What? Representative, right? Representative, and just return the request. Okay, so I have added one more line into the code. So what it does is basically uh let's say okay, just I'll explain it by drawing. Oops. How can I scroll to right? There is no scroll. There is this scroll, but yeah, yeah, yeah. Okay, I'll just refresh it, right? So let's say if I have something like this one, uh, two, three, and four, right? So if I have to find the parent of four, right? Parent of four, and the array is like one. Parent of two is one. Parent of three is one. Parent of four is two, right? Okay, what do I do? Whenever I am on 4, so index is 4, parent of uh, So I have to find the parent of 4, right? So it's equal to 2, right? So 4 is not equal to 4 basically. So what I'm doing is it will find me the parent, right? So I'll just update the parent of 4 to be equal to 1. So similarly 2 will be updated and path compression will be applied and we will get something like this. So this is one optimization we have done, path compression. Path compression optimization. Okay guys, give me 5 minutes. I'll come back after 5 minutes. Toilet break. So I'm back from the toilet break, and let's see if we are still live or we have gone offline. We are still go to live. Yeah, we are still live. Okay. So we have done path compression right here. Path compression optimization we have done here. Now the second thing is to do the optimization in union. So right. Hmm. So as I have already explained, uh, we have to hmm, so we find the representative u and we find the representative of v and we just make representative of u representative of v. But now instead of directly doing that, we will maintain an rank array. So I think we have to create another array that will be rank array, right? Rank is basically kind of height array, and what we'll do, initialize it rank, new int n, initially the height of high rank is called 1, and let's say, okay, so when I'm doing the uh, representation, right? So if rank of u, right, is less than rank of v, so basically rank of v is greater than, right? So we'll attach this. So this, right, this is true, right? We'll attach u to v because we have higher rank. So and rank will not be updated. As if the same thing, right? Rank of u is greater than rank of v. So uh, parent of representative of v is equal to u, right? Else. Now here comes the now which here now this means that rank of u is equal to rank of v. So here we will just we'll just attach parent of representative of u equal to parent of representative of v, and so I'm attaching u to v, and rank of representative of v will be increased by 1 plus plus. Right. So this is the second optimization we have done. Okay, so these are two optimizations we have done, and I think our data structure is ready. Ready. Uh-huh. So what's the question? Question. Give me question. This is simple. I think here the part optimization is done. Okay. So it's this time we have 02. So 0 is a friend of 2, right? 0 is a friend of 2. Okay. And 4 is a friend of 2. 4 is a friend of 2. And 3 is a friend of 1. 3 is a friend of 1. Okay. And check if 4 is a friend of 0. So 0 is a friend of 2. 4 is a friend of 2. So 0 is also a friend of 2. Oops. Check if, what's the question? Check if 4 is a friend of 0. 4 and 0. But to check if 4 is a friend of 0, it will be true, obviously. They are right. And if at 3, it will be false because 3 is not a friend of false. So that's true. That's true. Okay, so that's it. That is all about disjoint sets. It's kind of simple, right? So now we have understand it. So let's solve some problems. So on disjoint sets and the problems that I'll be solving, I'll pick it from the Striver graph series. So big shout out to Striver.
This is the best course I can say. It is perfectly fine.
Um, I'll take the problems from Strivers. So okay, so I think I have to understand Kruskal's algorithm also, and then there are some problems like number of provinces, number of operations to make network connected, account mode, number of island two, making a large island. Hmm. Okay, so I have to, I think, understand Kruskal's algorithm also. Okay, Kruskal's algorithm. What is system minimum spanning, right? Okay. Hmm. Hmm. So, so should we do it? Should we do this in this video, or we can? I think we can create another video for Kruskal's algorithm. So yeah, I'll just end this live